Hello, my name is Fazan. I'll explain the experimental procedure for the pipe friction lab. So the lab has two objectives. The first one is measuring the pressure drop versus flow rates, and the second one is observing the different flow regimes. For the first part, we have a test section pipe, which is a 1.5 meter pipe with the inner diameter of 12.6 millimeters. And these 2 points are the points that will measure the pressure drop between them. Okay? So here we can adjust the flow rates with these 3 valves, which are globe valves. And we have 3 rotometers, which are flow meters, for different specific regimes. And the largest one is for the highest range of flow rate, the medium one for the medium range of flow rate, and the smallest one for the lowest range. And for each rotometers, we will use different pressure indicator. For the largest one, we'll use wet digital manometer. For the medium one, we use U-shaped or inverted manometer. And for the lowest flow rate, we'll use capsulic pressure indicator. Yes, now I'm going to do the measurement. Firstly, before you use each flow meters, you should check that the pressure indicators are calibrated. So, for example, for this one, I'm going to start for the highest range of flow rates, which is the largest flow meter. Before opening the valve that is connected to this flow meter, we have to check the calibration. So, I'm opening the valves which are connected to the digital manometer, and then I turn it on by pressing and holding the on-off button. So if it's showing 0, it means it's already calibrated. If it's not, there's a button here that we can press and hold it and 0 the pressure. So it's already calibrated. And the valves are open. Now I can open the valve that is for largest flow rate, largest flow meter, which is highest range of flow rate, and I'm making it maximum flow rate. This flow rate is 1600 liters per hour. After we make this, so now I can immediately read the pressure drop from this manometer. So it's 17.2. And if it fluctuates, we can just take the average of the reading, but it's very close to specific reading. Then, after writing down the pressure difference and the flow rate, we'll decrease the flow rate by 100 liters per hour. And then we'll do the same thing. We'll read the pressure drop from here and we'll write it down. And again, this will continue with the same procedure. So decrease it by 100 and we'll keep going till we reach 200. Okay? So that's for the highest range. After that, we'll shut the valves, which are connected to this one, turn this off, and I'm going to do the second one, which is the medium one. So I'm opening the valves that are connected to this inverted manometer to check the calibration for this one. These 2 levels should be at the same position. And if it's not, it means there is bubble in the pipe, so the bubble should be removed. But if it's just 1 millimeter, it's okay, and we can take that offset. So I imagine that it's the same position. Now, similar to the other one, similar to the other one. I'm opening this valve and make it maximum. But maximum here is 250 liters per hour. And after you make this, you can immediately read the pressure drop from here. And here is in centimeters. Now I can see it's 7 centimeters. Then we're doing the same procedure, decrease it by 25 though. So here the step is 25. And again, immediately we can read that. So it's 6, the pressure drop. Then we'll continue the same procedure and decrease it till we reach 50. So here the step is 25. After that, we close that. Close the valves. And this valve as well. And we're going for the last one. The last one, which is capsulic pressure indicator and is for the lowest range of flow rate, is slow. So we need to wait for each reading. Even for the first time when there is no flow and we want to check the calibration, we open these two valves which are connected to the capsulic pressure indicator. So it's not 0, but it's going down to 0. So we need to wait for 2 or 3 minutes for each reading. So imagine I waited 2 minutes and it went to the 0. Now we're doing the same thing. Increase the flow rate to the maximum. Here is 70. And then we can read the pressure from here. So we had to wait, but we didn't. So for example, that's 50. And the last one, which is capsulic pressure indicator, is in Pascal, the unit of the pressure. Then we decrease it by 10. Again, we wait 2 or 3 minutes, and then we'll go to the other one and read the pressure. Till we reach 10. So I'll repeat it once again. For here, the step is 100. For the medium one, 25, and for the last one, 10. And also for the pressure indicators, we just write down the units. We just write down the readings directly with the units that we read here, because later we use a Excel file that automatically convert all the units to SI units. And also there is a thermometer here which we need to read the temperature, and we do it just once to find the physical properties of water, density and viscosity. And we need this for calculating friction factor versus Reynolds number. The other thing is to draw a schematic diagram of this rig. You should know all the components names and also the standard symbol which is available on the internet. So I'm explaining all the components and their names. So they are adjustable valves and they are globe valves. They are flow meters and their name is, the type is rotometers, but different range. Thermometer for the temperature. And all of these valves, which are on and off valves, they are ball valves. As I previously said, this is wet bed digital manometer, embedded manometer, and capsulic pressure indicator. And we have a dry solution tank as well. That's for the second part of the experiment. It contains some ink that will inject them to the pipe. So this should be included to the schematic diagram. And this valve is a ball valve, and this one is globe valve again. Okay, for the second part of the experiment, which is only done by demonstrated once at class, and you don't need to repeat it, is fluid visualization. So what I'm doing now is I start with a low flow rate. So I make the flow rate of water here very low. And then I'm opening the I'm opening the dye solution valve. Now we just need to look at this part of the pipe because the other part has the effect of the initial injection of the pipe. So now at very low flow rate, we can see how the dye solution is flowing in the pipe. It's very smooth. There is no fluctuation in the dye solution flow, and also there is no mixing between water and dye solution. And they are all the characteristics of laminar flow. So now we're in laminar region. By increasing the flow rates, for example, when we reach about 40 liters per hour, we can see the changes in the color of the dye. That's because the rate of mixing increased a bit and the dye solution become a bit thicker. That's because there is some fluctuations in it. So this flow is not laminar anymore. It's not turbulent neither. That's because in a turbulent flow, the flow is completely chaotic. Well, at least we can see a pattern here. So transient flow with some fluctuations, but it's not completely irregular. When I increase the flow rates more and I go to the high flow rates, and when I reach about 150 liters per hour here, I barely can see the dye solution. That's because the rate of mixing is too high, one of the important characteristics of turbulent flow. And so the mixing is high, we can't see the dye solution here. And the flow is completely irregular and chaotic. So that's the characteristics of turbulent flow. Okay, and that was the second part of the experiment, which we observed the differences between the three flow regimes: laminar, transient, and turbulent. Thanks.